Welcome to this video about Eulerian graphs. First, we're going to need a couple definitions before we can define what we mean by Eulerian. So let's talk about a walk in a graph. And these other ideas, paths and circuits, will be specific kinds of walks. A walk in a graph is a sequence, a sub 1, a sub 2, a sub 3, a sub 4, a sub n, of not necessarily distinct vertices in the graph in which each of the sequential vertices has an edge between it. So to write a1, a2, I'm saying there's an edge I can trace, like it could be t comma s. And then a2 would have to be connected to a3, so there has to be an edge between those two. And then a3 to a4 and so on. That's how Trudeau defines it. But intuitively, it's a list of vertices in a graph describing a list of incident edges that I can trace through. And the key thing is that these should be traced in the order given, so the edges have to meet one another. That's what I mean by saying they're incident edges, is that two sequential edges will have to actually touch, and therefore the sequential vertices must be adjacent. When we say the walk connects the starting vertex to the ending vertex. Here are two examples. So in this graph on the left, I have TSU, VU, TRS. Let's trace that out. T to S to U to V, back to U, so I want back, and that's okay because it's fine to repeat edges. Oop. And to T to R to S. So this is a walk from T to S that actually ended up using and overusing all the edges in my graph. Now, I can contrast that with the second list I have here, which is TSUR. So T to S to U, and then it's trying to travel to R, but there is no edge from U to R, so I would be making up an edge that doesn't exist. And that's not allowed. We can also talk about the length of a walk, that is the number of edges in the walk. So why don't we go ahead and count from the first walk how many edges that was. T to S, 1, 2, 3, 4, 5, 6, 7. This one had length 7. Along with the idea of a graph having a walk, we can talk about a path. Now, a path is a specific kind of walk. It's a walk in which we don't repeat any edges. So I gave two examples here. So unlike when I repeated this edge here from U to V, we're going to not do that this time. And so a path, TSUV, is a path from T to V, but that's not the only way to travel from T to V. I also could have traveled from T to U straight to V. So both of those would be paths. They don't repeat any edges. And the first one has length 3 because there are 3 edges, and the second one had length 2. Finally, we can have the notion of a circuit. Now, a circuit is a path that starts and ends at the same vertex. So let's look at some examples of that. The first one I have here goes around this triangle, TSUT. That's a circuit starting and ending at T. Another example would be the circuit that goes around the square, RSUT back to R. Both of those are circuits. So now we want to look at a specific kind of circuit, and that's an Euler circuit. So Euler is a famous Swiss mathematician who we'll talk about more, and in case you need to know how to pronounce it, it's Euler. So an Euler circuit is a circuit in a graph, so it's this tracing out of edges in a way that you start and end at the same place that includes every edge once and only once. So this means it's not just that you start and end and that you're not duplicating edges, but that you also don't miss any. Euler circuits will trace every edge of the graph, return to where they started to. And while they can't repeat edges, they may repeat vertices if a vertex has more than two edges starting and ending there. So let's go ahead, starting at H, and I'll show you an Euler circuit. We're going to start at H, and we're going to travel from H to G, and then we're going to go from G here to K, and then we'll go up from K to H. Then we'll travel this path here from J down to K. So notice we haven't duplicated any edges yet. And then K to I, and I back to H. Now one thing you'll notice actually is I started us at H, but we could reread the same sequence starting at I, and we will still get an Euler circuit. So let me get us a pen. I, H, G, K, H. This is the same one I did before, J, K, I. So an Euler circuit is a description of a list of vertices. You'll notice I never went over the same edge more than once. And when a graph has an Euler circuit, we say it is Eulerian. There's a similar notion to Euler circuit called an Euler path. An Euler path is a path in a graph that uses every edge once and only once. So remember, paths start and end at different places, typically, or at least they will in this case. So an Euler circuit will require us to have the same start and end, but with an Euler path, our start and ends will be at different places. And when a graph happens to have one of these, we'll say it's semi-Eulerian. So let me show you an example. Here we have a graph, and the following sequence of vertices, starting at C, will give me an Euler path. So here we are at C. I'm going to go from C to A, to E, to B, to F, to D, back to C, and then travel across through the last two edges here, C, E, F, and in this way I've traced every single edge, and that means it's an Euler path because I ended at a different place than I started at. Now, not all graphs are Eulerian or semi-Eulerian, so if a graph doesn't have an Euler path or Euler circuit, then it just doesn't hold this property. So here we can look at a couple of different graphs, and only one of these will end up having either property. So let's start out looking at the one on the top here. If you start trying to trace out all the edges, you'll notice you can come back to L, so I went around the outside here, and now I somehow need to travel through O 2 times, and I don't have a way to do that without repeating. So if I now go like from L to O to N, now I got to N and I'm stuck. That won't work. So maybe I'm supposed to travel through O all at first. So like P-O-N, L, O, back to Q. Uh-oh, now I sort of have the same problem. The 3 edges I have left to draw don't all connect. If I go from Q to N, I'm stuck. Or if I go from Q to P and to L, then I still can't get back and get QN. So this one has neither. Let's look at the one on the bottom left. Since we see there's one vertex that you can only start from, we should expect immediately there's no circuit. So it's not Eulerian. But why don't we keep tracing? Okay, so we got to U. We could go around the outside. But now I don't have a way to do that edge along. So this is also not semi-Eulerian. There's not an Euler path either. So in these first two, there's nothing. But if I look at the last one, I actually have a chance. So I can start at M, I can travel to I, And now remember the rest of this graph here, this is the part where I said there was a circuit. I actually took the one from before and I just added an edge to it. That means I'm going to be able to travel all the way through this graph, woo, and come back to I, and so I started at one place, ended at another, but at the end of the day, the full graph was semi-Eulerian. There was an Euler path. So we can see some graphs have Euler circuits, some have Euler paths, some don't have either. So what's up next this week is to find out when graphs do have Euler circuits or paths, talk about some applications of this, like why do we care at all? And then also identify some algorithms or procedures for finding the Euler circuit or path in a graph once you know it has one. And this will mostly be over the weekend. So there you go. Those are Euler paths and Euler circuits. Have some fun trying to find some.